Hey guys, we've got chapter 29, number 45 here, in which we're given a picture where a proton is being fired with a speed of 200,000 meters per second from the midpoint of the capacitor towards the positive plate. So it's going right initially. Part A asks us to show that it has insufficient speed to reach this positive plate, and it's going to go back towards that negative plate. Well, we know it's going to go back towards that negative plate by drawing the electric field lines on there. It's going to naturally want to go towards that negative charge. We've got our battery here, 0 volts here, and a 500 volt plate there. So in order to figure out if it's going to reach the positive plate or not, we need to determine the potential energy that it would have at 500 volts, and then as well the kinetic energy that it's going to have when it's released. So first I started by solving for the kinetic energy here, 1/2 mv squared, and got 3.34 times 10 to the negative 17th joules. That's the energy it's going to have when it's shot. In order to reach the 500 volt plate, we use delta U equals, the potential energy equals Q delta V. The change in the volts is 500 minus the midpoint 250, so it's going to be 250 volts here. And that's going to be 4.0 times 10 to the negative 17th joules. That's what the energy it would need to get to the positive plate. So since that number is larger than the actual kinetic energy that we solved for, we know that it's not going to have enough energy to reach that positive plate, so therefore the kinetic energy is less than the potential energy. And that's our solution to part A. Part B asks us to determine the proton speed as it collides with the negative plate. So as it's already done all of this and it goes back to collide with the negative plate, we're determining the speed as it collides with that negative plate. So in order to do that, we can use a law of conservation of energy here, and we'll have kinetic energy initial plus potential initial equals kinetic final plus potential final. Well, the potential initial is going to be 0, and the kinetic energy final is going to be 0 because it has no velocity. Potential 0, it has no height. So the kinetic energy initial we have previously solved for, 3.34 times 10 to the negative 17. Just plug that in down here into part B. Potential final is going to be 4 times 10 to the negative 17th joules. Again, it's the difference. It's the Q delta V. We just solved that right here. So that's going to tell us actually how much more kinetic energy is needed. So we have our kinetic energy and our potential energy. Well, we decided earlier that we had this much more potential energy than kinetic. So, sorry, this much more potential energy than kinetic. So in order to determine the final velocity as it reaches the plate, we know that this is how much more kinetic energy it's going to need, and we can set that equal to 1/2 mv squared to solve for a velocity. Now this velocity will ultimately needed to be added to the initial velocity to get the full velocity speed, but this is how much more energy is needed because it's a law of conservation of energy problem. We can go ahead and just start using the 1/2 mv squared here to determine that's how much more energy is needed to reach the plate, and then it'll transfer when it reaches the negative plate. So we'll get a velocity here once we solve out 1/2 the mass of the proton, velocity squared. We get a velocity of 88,905 meters per second. Well, that's how much more is needed to reach the plate, and if you add the initial velocity to that, we get 2.89 times 10 to the 5th meters per second, and this is our speed as it's crashing into the negative plate because of law of conservation of energy. So if this is the ultimate velocity at, I'll go back to the picture here, so that velocity is going to be right here. We know that because the speed here is going to be 0, but we determined how much more energy it needed to get to that point, so we can add that to the initial velocity and ultimately land us with a 2.89 times 10 to the 5th meters per second. Thank you.